Let us try to understand lexicographic ordering, the easiest way we can understand lexicographic ordering. And that's by looking at an example. So here you can see I've drawn yet another grid. And in this grid we have n equal to 3 because 1, 2, 3, and m is equal to 4 because, well, 1, 2, 3, 4. And let me just name the points along the x and y axes. I have x0 up to x4, and I have y0 all the way up to y5. And the main point with the boundary conditions is that we know the value of u in all of the green points. So green points in the green dots, ui comma j is equal to 0. And the purple dots, well, they are the dots in which we need to find ui comma j by solving our matrix equation. And instead of just finding ui comma j using the matrix equation we will solve is av equal to b, and then we will find a vector of v's, v1 all the way down to vm times n, which in this case is v12. And these values will in some way correspond to the uij's. And the thing is just now we need to make sure that we know when we say v1, v2, and so on, which point we're actually talking about. So the way we're going to start this off is to write the u's up first and foremost. So this is u11, this is u21, this is u31, then we have u, and then I have the x index is 1, the y index is 2, so u12, u22, u32, and I go on as such, u13, u23, u33, u14, u24, u34. Now, how do I write up the names of the v's? Well, with lexicographic ordering, the way we order stuff is first by the first letter, and then the next letter, and then the next, etc., etc. Wait, let me just try that again. With the kind of lexicographic ordering we have in the book, we actually order on the smallest letter first, so the first digit here, and then we go upwards. So you know what? It's just better if I write up which is which, and then you can just see the pattern yourself. So we lie down the v's one row at a time. So this is v1, this is v2, this is v3, v4, v5, v6, v7, v8, v9, v10, v11, v12. So as you can see, there are 12 dots, so we end with v12. And the way we go about this is we start with the smallest j coordinate, and we then grow the I coordinates, and then we go to the next j coordinates and increase the I coordinates, etc., etc. Now, a very useful thing for when you will be programming is to know how to translate between L and the I's and J's. So given an L, what is the corresponding ij index? And given I and j, what is the corresponding L index? Because when you do your implementation, you will be solving this matrix equation, which will give you a v1 to vm times n vector. But when you plot the graph, you will actually want to be able to know which xi comma yj each of the v's correspond to. So in order to know that, you will need to be able to translate between the l's and the I and j's. So let's start with the easy one first. So given I and j, so if we know what I and j are, then L is equal to j minus 1 times n plus I. So for example, if I have u1 point, no, that's a boring example. If I have u2 comma 3, then I can find the corresponding L index by saying, well, it's 3 minus 1 equals 2 times n equals 6, and then plus I, which is plus 2, so 6 plus 2 is 8, and that gives me V8. And if I check it up here, then we see, well, that answer was indeed correct. Now, given L, how do I find I and j? Well, the j is equal to the value of L divided by n rounded up. You can try and think a bit about why that's the case. And the I is equal to L minus n multiplied by the value of L divided by n rounded down. So let's try to look. For example, if I have V10, what does that correspond to in the terms of U? Well, let me start with the j part. That is 10 divided by n, which is 3. So 10 divided by 3 is equal to 3, and I round that 3 point something, and I round that up. I have to find the ceiling value. So that is that is 4. So j is 4. And then I take L, which is 10. So L is 10 and n is 3, and L divided by n was 3 point something. So I have 3 times 3, which is 9, and 10 minus 9 is equal to 1. So my guess is that V10 is equal to U1 comma 4. And let me check. Well, indeed that is so. So this is all I have to say about lexicographic ordering. And again, if you just read page 190 and 191 again and again, then the implementation part actually shouldn't be that hard. The only part that is left of 618A for us to look at now is the argumentation that your matrix A is positive definite. And in order to argue for that, there are certain concepts that we need to go through that are explained in the book, page 192 to 193. So let's take a look at that in the next couple of videos.